Okay, welcome back. So we were looking at this idea of using the proper motion of these knots in the supernova remnants to measure the expansion speed. So this is just like the same thing we were doing with proper motion for stars in the workshop 2. So you can work out how far the spot will travel in the plane of the sky over 1 year. So it was 0.15 arc seconds per year. So here's 0.15 arc seconds, convert to radians, multiply by the distance, which was 2 kiloparsecs. And so here's 2 kiloparsecs. So that gives you that number of meters. And then to work out the speed, then just distance over time. So it travels that far in 1 year, which is just over 3×10⁷ seconds. So that gives us this number of meters per second, which is about 1,500 kilometers per second. Okay, so here it's still quite a young supernova remnant, so still hurtling along at thousands of kilometers per second. Okay. Now, if it's been moving at that 0.15 arc seconds per year since it started, and it's been going and it's traveled 150 arc seconds in radius, then you can work out when it started. Okay, so the time taken to move an angular distance divided by angular velocity. So you've got 150 arc seconds at a rate of 0.15 arc seconds per year. So just divide those two numbers and you get a time scale in years, which is 1,000 years. Okay. So if we assume, if we just subtract that from now, then that would tell us that the explosion took place around 1020 AD. Of course, that assumes it's been uniformly expanding at that rate the entire time, and it's not quite spherical, and et cetera, so obviously it's not that accurate. But this is one of the supernovae that is actually recorded in sort of ancient history, as it were. Okay? So Chinese astronomers recorded this event in, well, lots of astronomers around the world recorded this event in 1054 AD. And so this is accepted as the actual eyewitness accounts of the explosion that gave rise to the Crab Nebula that we see today. So, still about 1,000 years ago. And, the reason that, because it's only 2 kiloparsecs away, this thing was severely bright. It appeared as a new star in the sky during the daytime. Okay, so it's that bright. So brighter than, the planet Venus that you can see very brightly in the evenings at times. It would be brighter than that. So basically this is referred to as guest stars or new stars. That's where the name comes from. Nova Stella as a new star, and obviously a supernova stellar is an even brighter one. Okay. So all around the world, people recorded the appearance of a new star in the sky during the daytime. They even mapped out where it was in the sky, and that fits with where the Crab Nebula actually is. So the Chinese did this, and the Japanese. You can see a copy of the historical Chinese record here. The Arabic astronomers in Iraq also recorded it. Native Americans recorded it a petroglyph. So you can see a petroglyph, a rock carving here. So here's the new star next to the crescent moon, which again, if you wind back the astronomical clocks, is about right. That's where it would have appeared relative to the new moon at the time when the explosion took place. And Aboriginal, it's also in the Aboriginal record in Australia as well. So yeah, so you can do historical astronomy too. Okay, so let's continue this story of what's happening to this hot bubble of gas from all of these supernova explosions going off. Like I say, every 30 years or so, one of these stars will be exploding in our galaxy. So over time, then these expanding bubbles eventually end up filling up quite a large volume of interstellar space in a galaxy like our own. Okay. Now again, the sort of the pressure equals n proportional to nt argument comes in here. it'll eventually come into sort of pressure equilibrium with the surrounding interstellar gas, the atomic gas. And so it will do that when it reaches a very low density at about 10 to the 3 particles per meter cube. So that's 1,000 times lower than the typical interstellar medium density at 10 to the 6. But it stays hot, basically. Once you've got gas that hot, it's very difficult to cool it down in space. So it stays at these million-degree temperatures. And if you observe an entire galaxy with a sensitive X-ray telescope, you can pick up all of this sort of hot gas emitting, filling up a large volume of a gas-rich galaxy like the Milky Way is. And you can see it in other galaxies. So you've got this, a whole galaxy will be full of this sort of diffuse X-ray emission. So diffuse meaning very extended source of X-rays, because you've got all of these bubbles of very extended hot gas everywhere. And it's basically due to all of these expanding supernova remnants. So quite a good picture of, to complete the sort of picture of the interstellar medium, is a bit like a Swiss cheese, okay, where the cheese itself would be the atomic gas, if you like, making up most of the mass, but in it are blown all of these big bubbles due to the exploding supernova remnants. So we can sort of see a little bit of that here in this picture. So this is a comparison of an optical picture of a spiral galaxy on the left with a X-ray picture, again from the Chandra satellite here on the right. Ignore all the little points of light here. What we're interested in is this red glow here, which is the extended X-ray emission from the hot gas in this galaxy. And you can see that it kind of follows the spiral arm pattern that you can see in the optical picture. Here's the spiral arm, this one going this way, and here you can see the same spiral arm coming up this way. Similarly on the other spiral arm, which is here, and in the X-ray picture you can see it here. Now of course that makes some sense, because all of these bright blue stars here are the massive stars in the spiral arm of a spiral galaxy, the population 1 stars. And all of those type 2 supernovae explosions will be basically when these stars explode at the end of their lives, which of course are also very short. They might only last 1 million years or so. So they haven't actually moved very far, so they're still in the spiral arms when they explode and die as supernovae. So you expect to see quite a lot of X-ray emission from the supernova explosions of massive stars in the spiral arms of spiral galaxies. Okay. So this is a good skill to get used to in this module as well. We'll have a workshop that sort of focuses a little bit on it in the future. Thinking about how the same object appears at different wavelengths, understanding why they look like they do. Okay, so X-ray emission is not the only way that supernova remnants can be found. They also emit very strongly at radio wavelengths, again. Okay. So here, again, we've got electrons that are being accelerated. So it's sort of similar to the Bremsstrahlung mechanism, but it's crucially different, because here, what's accelerating the electrons is the fact that there are magnetic fields present in interstellar space. So we haven't really mentioned this much. We've talked about magnetic fields on the sun, but just again, take it from me that there are magnetic fields out there throughout the whole galaxy as well. So threading through interstellar space. And when these supernova shocks come along, they tend to sweep up and concentrate the magnetic field ahead of them. At the same time, those shock waves are accelerating electrons up to very high relativistic speeds. So this has nothing to do with thermal motion of the electrons. This is now, again, being swept up by those fast shock waves. So that gives a population of basically relativistic electrons moving in a strong swept up magnetic field. And this gives rise to a different mechanism that is referred to as the synchrotron radiation. Okay, so again, hopefully you come across the idea that, as I think we've mentioned before, if you've got a magnetic field line and a charged particle, I'll try and keep still, then the charged particle will experience a force and start to circle around the magnetic field line. Okay. So they spiral around the magnetic field lines, and each time they're spiraling around, they're being accelerated. And so an accelerated charge, like an electron, again, will give rise to electromagnetic radiation. And again here, in this case, it appears in the radio part of the spectrum. So here's a little sketch. So here's a magnetic field line, okay, and here's an electron that's come in and it's been sort of captured by the magnetic field line and it's now spiraling around. But because it's basically in circular motion now, it's constantly being accelerated and therefore constantly emitting. Of course, this is again another form of continuum radiation, because depending on the speed of the electron, the strength of the magnetic field, and how close it was, then you'll get a different acceleration, which gives rise to a different frequency. So here is a beautiful image that we can show both of these mechanisms in operation. So the red is X-rays, like we talked about before, because of the hot thermal electrons and bremsstrahlung inside the nebula. And here, right all the way through again on around the edge hold on, I've got that the wrong way around. So sorry, the blue was the X-rays, the hot shocked gas at the edge. The radio is the red. Okay. And so this bubble is filled with radio emission. So that's the electrons spiraling around in the compressed magnetic field. So again, it's concentrated around the edges again, which is where the fast electrons coming out of the shocks and the swept up magnetic fields exist. So synchrotron radiation, that's another key mechanism. So again, get familiar with mechanisms, emission mechanisms during this. We've had black body radiation, we've had bremsstrahlung emission, we've had spectral line emission, and now we've got synchrotron emission. So I want to distinguish a little bit again between the thermal bremsstrahlung emission coming out of H2 regions and this synchrotron radiation coming out of supernova remnants. They are both in the radio wave band, but the synchrotron gets stronger and stronger at even longer wavelengths. So long wavelengths up at around about 1 meter. So the longest wavelengths we're going to look at in this module. And it's very much what we would call a non-thermal emission mechanism. So the electrons that are giving rise to this emission are not moving around with their normal thermal speeds associated with the temperature of the gas. They are going much faster than that because of this shock phenomena that is accelerating them way past that. So synchrotron is a non-thermal mechanism, whereas the thermal bremsstrahlung is a thermal mechanism. And I'll show you a graph in a moment to show you the different sort of emphasis, different wave bands within the radio that these two mechanisms are strong in. And this allows us to distinguish between different types of radio emission out there when we're mapping radio sources. So let's just cut to this diagram. So here we've got, these are still spectra, basically. You've got flux against frequency here, but I've put wavelength on the top as well. So wavelength obviously going the other way from frequency. So this is long wavelength, low frequency, shorter wavelengths, higher frequencies. So you might recall that I showed you the Orion Nebula, a radio emission from the Orion Nebula before, and told you that it is strong at sort of centimeter wavelengths. So you can see the flux rising up here, getting strong at centimeter wavelengths. Whereas a supernova remnant like Cas A, the one I showed you the movie of earlier, is getting stronger and stronger as you go to longer wavelengths. So it's very strong here at meter wavelengths. Okay. And that distinguishes between the non-thermal synchrotron mechanism, which increases this way, and the thermal bremsstrahlung mechanism, which increases this way. And so here's another composite picture. This is going to sort of take us forward in the module a little bit as well. So now the blue is radio emission at around about a meter wavelength, and the red is actually infrared emission, okay, which we haven't really come onto yet, but let me just illustrate this. So this image contains both supernova remnants and H2 regions. Okay, so the supernova remnant is the main source in the middle here. Again, you know, it's not like a perfect bubble, but you can see there's a sort of bubble of synchrotron emission here in the center of the image, which doesn't have any of the sort of red emission associated with it. Okay, so that's a supernova remnant. But this emission here, this is an H2 region. So this is a bubble of H2 region emission, and it's surrounded by infrared emission. And this is the infrared emission here is due to warm dust in a molecular cloud. Now we're going to come on to the dust in the next lecture. Okay, so again, similar over here. This is an H2 region. This is an H2 region, but this is a supernova remnant. Okay. And again, this is very strong at these long wavelengths, whereas the H2 regions are a bit less strong in the radio, and also associated with dense molecular dusty material. That's what you'll see. Okay, so just to finish up, I want to just compare and contrast a little bit, come back to where we started with these two types of supernovae. And here the notation gets even more confusing, so apologies for that. So that you remember the type 2 supernovae come from the massive stars exploding, but of course the massive stars are part of the population 1 stellar population, and they occur in spiral arms and irregular galaxies. Okay, so the type 2 supernovae come from the population 1 stars, and as sure as night follows day, the type 1 supernovae actually arise from the population 2 stars, okay, because type 1 supernovae are coming from these old white dwarfs that are getting pushed over their limit. So white dwarfs will have evolved from sort of stars similar to the sun, so they will be 10 billion years old or so. And so they're in the old low mass population. That's where they've come from. And so they would be associated with population 2. So they might come from the bulge of a galaxy, like a spiral galaxy, or even in the halo of a galaxy, which we haven't really come to yet, like a globular cluster. Okay. So let's summarize all this. We have quite a lot in there. So supernova remnants. So the main takeaway points here, one of the main sources of energy input to the interstellar medium. So especially in terms of this kinetic energy. Okay, so you've got these very energetic bubbles hurtling out through the interstellar gas all the time and really stirring everything up. I want you to come away with this picture that the interstellar medium is not some sort of benign set of clouds gently floating around. They are constantly being buffeted by the supernova explosions. Everything's rotating around in a spiral galaxy, so there's constantly being sheared. You've got gravity trying to pull it together and form new stars. So there's a lot going on in the interstellar medium. It's a very dynamic place. Might take a long time, but there's a lot going on, and it's very important for the evolution of galaxies. So these supernova remnants, we can trace them by looking at the X-ray emission from the hot gas, the thermal Bremsstrahlung emission, or we can use sort of long wavelength radio, sort of meter wavelength, to map out their synchrotron emission from these relativistic electrons being spun around in their magnetic fields. And I guess a point I didn't make too much actually, but you can really think of them as almost a separate phase of the interstellar medium. Okay, so this completes the story of the gaseous phases of the interstellar medium. So remember, we had H2 regions, the ionized gas at 10 to the 4 Kelvin around massive stars as they're forming and still surrounded by their molecular clouds. So the molecular clouds, which are dense but very, very cold at 30 Kelvin. And then the rest of the mass of the interstellar medium is made up by these atomic clouds, around about 100 Kelvin. But blowing holes in all of that are these supernova remnants, which are up at 1,000,000 Kelvin, very low density. So they're the holes in the Swiss cheese of these galaxies. Okay. So to give you an idea of how big these holes in the Swiss cheese actually are, then here's, again, just a simple little problem this time to leave you with. So I mentioned that these supernova remnants will keep expanding for about 1 million years at an average speed over that lifetime of about 100 kilometers per second. So how far will they have traveled in that time? So that will give you an idea of sort of the influence of these supernova remnants. Okay, so next time we'll start to focus on another key component of the interstellar medium, which is the fact that mixed in with all of this gas are interstellar dust grains, and that's what we will look at next time.